What we're looking at in this video is conversions between hexadecimal and binary and the other way around. And just before we take a look at that, there is a way that we can do this very, very easily by having a think about how hexadecimal and how binary works. Imagine that we're looking at 1 byte of data. So 1 byte of data is 8 bits. Okay, so here's our 8 bits here, and this would be the 1s column, the 2s column, the 4s column, 8, 16, 32, 64, and 128's column. Now this is quite interesting. Let's say that we have, and we just use half of this, we just use 1 nibble, so up to the 8's column. Let's say that we have the number here, 1111. So that's 8 plus 4 plus 2 plus 1, which is 15. Just remember the number 15 for a second. Then let's say that we use the whole byte, so we also add on to this the other parts here, but this time we don't use the first part. So this number here, which is 128 plus 64 plus 32 plus 16. So that's 8, 12, 20. And then that's 3, 6, 12, 14. And the 1 goes there. 140, and just remember that number as well. So we've got the numbers 15 and we've got the numbers 140. And then also, if we were to just erase these zeros, so we'll do these as all 1s, and what number is that? Well, when they're all 1s, we know that that number there is 255. Now these numbers here I'll just leave up because they could help us when we look at hexadecimal numbers. In hexadecimal, let's say that we have 2 digits. Well, FF happens to be 15 times 16 plus 15, because F is 15. So that's 15 times the 16's column. Remember, that's the 1's column and the 16's column. So it's F, which is 15 times 16 plus 15 times 1. So it looks like this. Now, 15 times 16 happens to be 140. This is the same number that we saw before happening. And then this 15 here, which is the second digit here, happens to be 15. And both the digits, FF, if we add those two together, 140 plus 15, we get 255. And look, there's that magic number again. So these 4 digits of binary here and these 4 digits of binary here perfectly correspond with the first digit and the second digit of hexadecimal, which means converting between hexadecimal and binary is actually incredibly easy. And let's have a look at how we do it, because it's got to be one of the easiest things you can do. So let's take a number, and we will take the number of a binary number of 01001011, and we want to convert that to its hexadecimal equivalent. So what is this number in hexadecimal? Well, the first thing we want to do is we want to split it up into 2 nibbles. So there's our first nibble, and that will be our second nibble. So the first nibble here, we now go as 1, 2, 4, 8. So what's this nibble here? Well, it's just 4. And our second nibble here is 1, 2, 4, 8. Our second nibble will be 8 plus 2 plus 1, which is 11. Now remember, 11, 10 is A, and 11 is B. So 4B is the hexadecimal equivalent of the binary number 01001011. Now it is of course possible to check that your answer is correct by converting them both to denary, just to double check. So this time we're not going to treat them as nibbles, so this will be the 1's column, 2's, 4's, 8's, and then the 16, 32, 64's and 128's column. We only did these as 1 to 8 because we were using them as nibbles. So this time we've got 64 plus 8 plus 2 plus 1. That number there is 12, 14, 15, and 6 plus 1 is 75. So in denary, this would be the number 75. And we want to check that this hexadecimal number is going to be 75 as well. So it's 4 times 16, which is 64, plus b, which is 11, and that gives us 75 in denary. These two numbers match, so we've double checked by converting both the binary numbers to denary. We've double checked to see that our answer is correct. Let's just do one more of these conversions, and this time we'll convert from hexadecimal into binary, just to show how easy that is. So I want to convert the hexadecimal number, and remember these numbers are quite big, so I'm only going to use 2 digits or 2 nibbles of data. And so I want to convert the hexadecimal number of 72 in hexadecimal, and I want to convert that into binary. So first of all, do the nibbles, so 1, 2, 4 and 8, and the second nibble of 1, 2, 4 and 8. So 7, it's not 8 can't go into 7, but 4 can, so we need 1, 4, 5, 6, 7. So that's what our first nibble looks like. And the second nibble will look, 8 can't go into 2, 4 can't go into 2, 2 can, and we don't need any more. So that's 2 there, and then 4, 5, 6, 7. So that's our 7 and our 2. And that there is the answer. Double check. So 7 times 16 plus 2 times 1. So the 7 times 16 is 112, plus the 2 times 1, which is 2, so that equals 114 in denary. And just double check to see what this equals. So this time we're not treating them as 2 different nibbles to get the hex, we are treating them as, instead, we are treating these ones here as a full binary number. So it's 1, 2, 4, 8, 16, 32, 64 and 128. So we've got 64 plus 32 plus 16 plus 2. So 2, 4, 10, 14 and 9, 10, 11, and that's our denary number. 114 is equivalent to 114, which means that that binary number is equivalent to that hexadecimal number. And that's how easy binary and hexadecimal numbers are to convert. And all you need to remember is that in 1 byte you've got either 2 nibbles, so 8 bits, 8 binary digits to make up a byte, or you've got 2 hexadecimal digits to make up 1 byte of data. And that's why it's so easy to convert between the two. And because we can represent a binary number perfectly as hexadecimal, and it's very easy for humans to read hexadecimal, that's why very often we'll use hexadecimal instead of binary.